Okay guys, today I wanted to talk to you about this kind of awesome connection between geometry or algebra 1, algebra 2, whichever course you're taking right now, and kind of how two of the main big ideals from those subjects overlap. So today we're going to be talking about the terms translation, reflection, and the three different types of asymptotes: horizontal, vertical, and slant. So the first thing I want you to notice is, based on this composition of a polynomial equation, this is actually a divising composition, right? We have the initial polynomial over a binomial. We're going to have three different sorts of asymptotes, or lines, where our graph cannot touch or go beyond, that kind of form from this graph, right? So we have our horizontal asymptote at y equals negative 31.784 and negative 0.784. So we can already see sort of a slim connection between these 2 points. I've elucidated them on the graph here. They're the points that run side to side where our graph can never touch or cross over. We also have a vertical asymptote at x equals 5. We can find this by placing negative 5 into the bottom of our initial equation here, and that shows that we'll end up dividing by 0, which we all know will make math explode if we do. So that's going to be another point we can't transgress, and I showed that right here. So what's really cool, though, is we can find a slant asymptote, or we call this an oblique asymptote if you want to be technical, if we actually divide out this polynomial using synthetic long division, right? Synthetic long polynomial division. And we're going to find the equation of that line to be y equals x minus 11. And what's really cool about this is the first thing you're going to notice is this resembles a linear equation that you may have seen before, y equals mx plus b. And that's actually going to be this very faint green line running through the rest of our graph there. So that's another point that our two parabolas we can see here can't touch or cross over. So if we take this extension of linear reasoning here, it's actually pretty cool because we can see that these horizontal asymptotes, they actually have an undefined slope because we don't have any motion in those, right? They're just touching that y-intercept. Same thing with our vertical asymptotes. We have a slope of 0 because there's no change in our x values. And we can actually see here that each of these lines has to have either an undefined or a slope of 0 or a slope of 1 over 1. That means all of our asymptotes are either parallel or perpendicular. And what's really actually super cool about this is that each point is either a translation or a reflection of themselves. We actually see the parabola reflected relative to the positive and negative values, which we can find using the square root of x, as we can see the leading coefficient, or the leading power, I should say, in our main equation is the power of 2. So every line on your graph can be mapped, every asymptote, I should say, can be mapped with a linear translation. Hey guys, just a supplementary addition to my last video, and that's not a pun on the supplementary angles which form here, but we'll discuss that in a moment. Just a quick review. In my last video, we described how we can map a horizontal asymptote, a slant asymptote, and a vertical asymptote onto our graph in order to find these linear projections of points where our graph could not touch or transgress. And it was very clear to see the slant asymptote at y equals x minus 11 as being a linear function, right, in our form y equals mx plus b. But we were also able to describe the slope of our horizontal asymptotes and the slope of our vertical asymptotes as undefined and 0 respectively, depending or not whether we cross the y or x axis. So, and we also described these two parabolas as reflections across this kind of slant asymptote, right? Because whenever you're performing a reflection in geometry, you can usually map that down to a system of collinear points which will lie upon the same line, right? And what you can also do is, if you drew extended lines from those points, since they have the same slope, you could draw parallel lines from those reflected collinear points. Now, what we're going to see further now is that since we have this slant asymptote at y equals x minus 11 with the slope of 1 over 1, we can actually map out another line, treating our vertices as collinear points, and we'll see that if we have horizontal asymptotes at negative 0.784, which will be this top point up here, and at negative 31.784, we're following that same slope formula. Every time our x increases by 1, so does our y. I just kind of represented it to you a little bit backwards there, because generally you'll start with the negative for counting, right? And one thing I also wanted to show is now that we've mapped out each of our asymptotes, we actually have formed systems of supplementary angles, complementary angles, interior angles, exterior angles. So we have set up a geometric system with which to represent our kind of composition of a divising polynomial problem here. So whenever you're looking at these polynomial problems, always look for what geometric structure you can add to them. It was based back in the Greeks where they started all of their math with geometric ideas. It wasn't until you got into the Middle East very, very early on, the Fertile Crescent, where they started to have more farming, more crops, more of a civilization, and it took more time to deal with abstract algebra. But everything had to start somewhere, and just as Rome wasn't built in a day, neither was the theorem of mathematics, right? So whenever you become confused about an algebra problem, always look to what sort of geometrical representation you may bring to it. Whether it's supplementary angles, whether it's linear relations, whether it's bisectors, and whether it's parallel lines. And just one more video because I feel like I didn't cover it in the last two. If we view our linear equation for our slant or oblique asymptote, our y equals mx plus b, in this case it's y equals x minus 11, and we find that oblique or slant tangent line, and yes, we're using a calculus terminology here, and we can actually find the y-intercept negative 11 of this slant asymptote as it crosses the y-axis and follow its slope up 1 over 1, up 1 over 1 as we continue on to infinity. So what's really cool about this is since the slant asymptote is itself a derivative line, right, a tangent line, we can take a derivative from our original equation utilizing L'Hopital's rule, and we can find that the derivative of our first equation is going to be 2x minus 6 and x, or we can get 2x minus 6 over 1. So because what we're going to do is we're going to take that 1 first power to the x, times it by the coefficient in front of the x, and we're just going to be left with 2x minus 6 over 1. So really we don't need the extra 1 under here. It's just a nonsensical divisor, right? But whatever we put in for x now, we just solve the top part of our composition of polynomials equation, and then we divide that by 1. So if I put 2 in for x, I'm going to end up getting negative 2 divided by 1, and I'm going to have a derivative there at negative 2, at 0.2. And when you go back to our graph, at 0.2 for x, pretty close to around here, we're going to have a derivative of negative 2 as we reach down to kind of get towards that asymptote, right? So what's really cool is you're going to be able to find relations between the slant asymptote, which is a tangent line to your parabolas, and you're going to be able to find a relation there between the limit function if you solve it algebraically. So not only is there relations between geometry and algebra, but also since calculus is pretty much just built up from algebra, you're going to find connections between geometry and calculus as well. So one thing I'm going to ask you to always do is to find and build these connections from your mathematics homework. Not only is it so much more interesting to learn why things work and how they're interrelated, but it's going to help you remember and recall them so much more.